Hey, welcome back. We're still working on the rotary table, and as you can see, it got scraped in the meanwhile. I had this rotary table with me in Denmark to the Richard King scraping class, and I finished all the scraping on it, and it came out quite okay. As you can see, the tabletop is scraped. The rear surface is scraped. The bottom surface is scraped square to it. And the bearing surfaces in here are scraped too. Let's talk about what I did. First, I scraped this surface parallel to the bore, and it was quite easy to measure this. I just I placed it on a surface plate, and I used an indicator in the bore in a surface gauge to check if the bore is level to the surface plate. Once I got this surface level to the bore, it wasn't off very much. It was about 1.5 hundredths of a millimeter over this distance. Then I scraped the rear surface square to the foot. After that was done, I scraped this bearing surface here parallel to the rear surface, because it's easy to check this on the surface plate for parallelism or with a micrometer. And then I used the housing as a master to scrape in the table itself. And I will show you a picture of the table when I glued it up first. And it had 3 high spots, and I guess that they clamped the rotary table in a 3-charge chuck when they machined it. And I clamped down on it hard enough to warp it during machining, and when they unclamped it, it relieved. It went back and had 3 high spots. So I scraped it perfectly to the master. Then I scraped the tabletop parallel to the bearing surface and parallel to the rear surface of the housing. It was quite easy to scrape this guy because it was already machined very, very precisely, and that's an important thing to note. Scraping goes so much faster when you invest the time forehand and do the machining very accurate. If you're off 5 hundredths of a millimeter or more and you have to scrape it out, that takes some time. But if you, especially when you step scrape it and have to tip in angles or parallelism, if you machine it already pretty darn close, which can be done on a milling machine, it's easy to hit 1/100th of a millimeter in parallelism on a well-trimmed milling machine. Then the scraping goes incredibly fast. So let's go to the surface plate and take some measurements. Okay, I set the rotary table up on the surface plate, and I have an indicator reaching down on the surface plate right here, reading 1/100th of a millimeter per division. And I'm just going to spin the rotary table with the indicator around, and you will see the deflection, or not the deflection, how much it is out of parallel between the bearing surface and the tabletop. So I set up a camera that looks down on the indicator, obviously, so ignore that, doesn't belong to the setup. So let's go around in circles. "90 degrees. That's about That's not even 1/100th of a millimeter. Let's go on. And I have to shift the rotary table a little bit on the surface plate because it is too small to sweep such a large radius. Going back to start. Ugh. There we go. Back to 0, and I bumped the indicator slightly, but goes to show that the tram of the table surface to the bottom surface of the rotary table is pretty darn good. And we were sweeping a circle with about 3/100th of a millimeter in diameter. So we are out of tram 1/100th of a millimeter over 3/100th of 300 millimeter diameter. That's not too shabby for my money. I guess that I will leave it that way. Okay, let's do a second test. We're checking the overall flatness and parallelism to the surface plate. So I got my 1/1000th of a millimeter indicator here in the height gauge, and I'm using a gauge block down here to bridge, for one, the grooves that are cut into the rotary table and also the scraping valleys, because those are up to 200ths of a millimeter deep, and that would give us a horrible reading on the indicator. That's the reason for the gauge block. So we start over here. And we zero our indicator out. Okay, let's write it down. 0 here. Now we move over here. This is minus 1/1000th of a millimeter. And this is minus 3. So we are well below 1/100th of a millimeter overall parallelism between the top surface and the rotary table, and also the tram of the rotary table to the bottom surface is good enough for my shop. It's not jig bore accurate, but it's good enough for a milling machine. Okay, I'm cutting the spiral oil groove on the hardened bushing, and I'm doing this on the lathe. I set up my tool post grinder with a carbide burr that has a rounded nose, and I already cut a groove all the way around. And I set the pitch for threading on this machine to 10 millimeters per revolution. So this is quite a steep thread that we're going to cut. So I'm spinning the chuck by hand, otherwise I run danger of hitting the face here, which I don't want to do. And yeah, we're just going on. There we go. That went quite well. I went down 0.4 millimeters deep, and that should be plenty enough to get the oil spread around the spiral groove. I have to be careful to clean out all the hardened metal chips before I reassemble the rotary table, otherwise they can cause pretty heavy wear on the surfaces. Same for the lathe. You don't want to get those fine hardened metal chips anywhere close to your moving parts. Moving parts of the lathe, of course. I took the housing, the casting of the housing, and I rested it on the bearing surface with two parallels, which I checked before with an indicator, on the surface plate. Now I'm checking the parallelism between the bearing surface and the surface where the adjustment nut for the axial play runs on. And I'm using an indicator on a stand, and I have this cast iron brick, which was in fact the practice piece we got at the stripping class, and it's a convenient heavy piece of iron that's flat that I can use as an indicator stand now. And I ran the indicator around the surface and checked for a deviation. Okay, the numbers. Let's get the indicator out of the way. The numbers are in 1/1000th of a millimeter, so maximum deflection is 3/100th of a millimeter. And from here to here, it's the plane of the surface is like this. It's tilted up on this side. And that's bad, because this is where the adjustment nut rides on. So I'm going to put this back on the milling machine and use the boring head with the auto facing function to clean up the surface perfectly parallel to the bottom surface. Okay, that's the setup I'm going to use to clean up the rear surface for the nut to ride on. I took a big box parallel, which I checked for parallelism on the surface plate before. I dropped the casting on it and I clamped it down in two places. Set up my boring head, the wool hop the boring head, for facing with a tool on an angle sticking out to the side. And right now I'm using the indicator to check my tram again before I start, just to be sure. Otherwise it's plain guessing. If you don't check it, you don't know what's going on. So, and the nice thing about the Indicol holder, of course, is I can use it with the tool in the spindle, and I have not to disturb my setup to check for tram or run out or whatever. Okay, this should be well within 1/100th of a millimeter. Now I can bring down the quill, set the boring head for facing by pulling this pin, bring the quill down. There is very little clearance all around the boring head, so I have to be careful. I'm running at 100 RPM. Okay, I have the rotary bagel. I have the rotary table back together, and I did a few minor things to it. The locking handles had a steel ball on the end, which was machined as one piece. I turned down the steel ball and took some screw-on plastic balls, because the balls always bounce here against the rotary table and they dented the circumflex of the rotary table, and that I don't want that, so plastic handles it is. I took the lousy sheet metal zero marker, threw it away, and machined one out of 2mm tool steel with a nice crisp engraved zero marker. And I took a piece of O2 tool steel, hardened it, and ground it down as a key for aligning the rotary table in the slots of my milling machine. I ground it actually to 14.029 millimeters, plus minus whatever. Yeah, and it's a ridiculous tight fit in the slot, actually. But that's what I was shooting for. Screws in place, and it can stay in place because it does not interfere when the rotary table is in horizontal position. And this is the locking screw which locks against the eccentric bushing for the worm, and this is a steel screw bearing against cast iron bushing, and that's of course a bad design because the steel screw will tear up the cast iron bushing, the surface. It will get all dinged up by the screw. So I took a piece of copper round material, cut off a very short piece, and dropped it in the hole so the screw clamps via the copper on the bushing. One of the last things I wanted to do is to check and maybe fix the Morse taper 2 socket in the center of the rotary table. I know that this has a little bit of runout, so we'll try to fix it with a Morse taper 2 REMA. First we will check the taper, or the runout of the taper, with a test bar. For that purpose I already cleaned the Morse taper in the rotary table, and of course I cleaned the test bar, and we will just seat it lightly in the taper. No need to hammer it home in the taper socket like crazy. And I have a 1/100th of a millimeter dial test indicator here, and we will do this very scientific this time. I will map out the error. We start here as 1, this is 2, 3, 4. We will take a measurement down here and up here, and that will give an indication not only on the runout, but also if the taper is skewed or tilted to the rotational axis of the rotary table itself. That means anything that you put in the taper socket will be on an angle and have a horrible amount of runout on the end. But if the runout is on both ends the same, we know that the taper is straight but off center and parallel. So let's check the runout down here. At 1 we have 0. At 2 we have -1/100th of a millimeter. At 3 we have 0. And at 4 we have 1/100th of a millimeter. +1. So that means +1, and over here we have -1. That means that the axis down here is shifted 1/100th of a millimeter parallel over there. And here we have 0, 0. Now we move the indicator up here. Go to 1, 0 this guy out, and do the same test again. We start at 0, go to -1, plus 0.5, plus 1, and 0. Back to 0. We are now at 0 again. So that means within the limits of this measurement that the whole axis of the Morse taper socket is shifted 1/100th of a millimeter off center this direction, +1 up and down. But it's parallel to the axis of the rotary table. That said, I want it to be on center as good as possible. So we're going to take this down, take the Morse, take the test bar out, and flip it back down. We want to move the whole Morse taper this direction, 1/100th of a millimeter. And we will do that with the Morse taper reamer. We will insert it in the socket, lube it up, a little bit of oil, and give a little bit of pressure with the finger up here, close to where it's cutting. And we will take a few turns, then we will release the pressure, pull it back a little bit, drop it back in, spin it a few times, so it relocates its center a little bit, and then we will check it again. That's not the perfect method, but I had very good results even reworking milling machine spindles that way. You would guess that you are more tilting the taper with this technique, and you can, but if you're careful and you let it recut its center each time you do this, you can actually move the taper socket parallel off center or back to center, whatever your goal is. Maybe you want to have an off center Morse taper. And using a Morse taper reamer is really, it needs a lot of finesse, I think. If you press down too hard on them, they will seize in the hole and tear really ugly holes, so we have to be very careful. It's not as critical as we have cast iron here, which tends not to grab as much. So let's give it a few spits. Okay, I gave it about five half turns, and while I was pressing with my finger in the direction I wanted to go, I also pressed down with my wrench slightly, so it actually cuts and does not only chatter over the surface. So now we take a few cleanup turns. Otherwise you end up with an oblong sized Morse taper, which is also quite useless. And when we look at the reamer, we can see that we actually took off some material. And the Morse taper was not very good on the surface finish to begin with, so that's a good thing. Okay, let's check the run out with the 1/1000th of a millimeter Mitutoyo Hikator. we start here at pretty much 0. And over here it drops down to -0.003 of a millimeter. And I think my indicator is broken. Yeah, I don't get any proper reading here. The movement on the hysteresis I get from the runout here is obviously too small for the elasticity in my setup and the measuring force of the indicator. So I guess it's pretty small. But it's touching in both directions. Goes to show that a normal indicator stand, no matter if it's a Fisso or a Noga or a Herger and Gessler, is completely useless when you use a 1/1000th of a millimeter dial test indicator, or dial indicator in this case. Had to change to the Mitutoyo height gauge, which is a very rigid setup for measurement. This works way more reliable. I think we can call that 0.005 of a millimeter, and I'm actually already 20 millimeters away from the surface of the rotary table. Out here it should have gotten also a little bit better. Okay, let's see. $5,000 down here, 1/100th of a millimeter in 100 millimeter distance. I think that's okay. I think the rotary table is done by now. I repainted the housing with the same gray I use on all my tooling that I rebuilt. I made a new brass badge. I will show that to you later. And yeah, it's done. I mounted it to a rotary table. It's indexed by the key in the T slot, and it's good to go. One last thing I wanted to show you, how square the rotary table is to the travel of the machine by running a dial indicator across the face of the rotary table. Otherwise everybody will ask in the comments how square I got it in the end. I got the 1/100th of a millimeter dial test indicator set up against the face. Now we're just traversing the y-axis across the rotary table. Okay, this is roughly 1/100th of a millimeter over the whole diameter of the rotary table, including the error of the milling machine itself. So I think that's pretty darn good for just dropping the rotary table into the T-slot and tightening it down without even dialing it in any way. So for 99% of the work I do with this rotary table, I think the registration with the key is good enough. And finally, here you have the new plaquette showing horizontal vertical 150 millimeter P for precision. The original maker Vertex back in 2015, and the rebuilt by me in 2017. So I hope you enjoyed this rebuild project or improving project. Thank you all for watching and see you next time.